Hello everyone, and welcome to Dr. Carminati's YouTube channel. I'm thrilled you're joining me today as we dive into an incredible topic from a recent Nature article titled, Scaling and Networking a Modular Photonic Quantum Computer. You can find the link to the paper in the description below. It's a fascinating read. I suppose you're as excited about the future of quantum computing as I am. In that case, I'd love for you to share your thoughts in the comments, suggest ideas for future videos, give this video a like, and hit the subscribe button to join our curious community. Let's explore this groundbreaking work together and uncover how photonic quantum computers might change the world. Today, we'll explore a revolutionary advancement in quantum computing, as detailed in the Nature article Scaling and Networking, a Modular Photonic Quantum Computer, published on February 27, 2025. The researchers, led by H. Agayi Rad and a large team, introduce a photonic quantum computer named Aurora, built from 35 photonic chips. Their work marks a significant step toward creating a scalable, fault-tolerant quantum computer using light, specifically photons. If you're new to quantum computing, don't worry. I'll break it down and guide you through this exciting development. Let's start with the basics. What is quantum computing? Unlike classical computers, which use bits to represent information as zeros or ones, quantum computers use quantum bits, or qubits. Thanks to a property called superposition, qubits can exist in a combination of 0 and 1 at the same time. This allows quantum computers to perform many calculations simultaneously, potentially solving problems like simulating molecules for drug discovery or optimizing complex systems that would take classical computers millions of years. Now, why use photons for quantum computing? Photonics, the science of light, offers unique advantages. Photons, the particles of light, can travel through fiber optic cables with minimal loss, making them ideal for networking. They also operate at room temperature, unlike other quantum systems that require ultra-cold environments. Plus, photonic components can integrate onto chips, similar to those in your smartphone, allowing for mass production. The researchers highlight these benefits, noting that photonics provides a promising platform for building scalable quantum computers. However, building a quantum computer isn't easy. Current systems, often called noisy intermediate-scale quantum (NISQ) devices, suffer from errors and can't yet tackle practical problems. The ultimate goal is a fault-tolerant quantum computer that can correct errors and run complex algorithms reliably. The paper explains that achieving this requires reducing qubit error rates below a certain threshold and scaling the system to handle many qubits. Aurora, the system in this study, takes a big step toward that goal by demonstrating a modular, networked architecture using photons. The researchers built a scale model of a quantum computer called Aurora, using 35 photonic chips connected by fiber optic cables. Aurora combines all the essential components for a universal, fault-tolerant quantum computer. Let's break down its key parts and how they work together. Aurora has three main stages: the source, refinery, and quantum processing unit, QPU chips. The source chips, 24, generate special light states called squeezed states, which are the starting point for creating qubits. A laser pumps these chips, producing entangled pairs of photons known as Gaussian states. Photon number resolving (PNR) detectors measure one photon in each pair, heralding a non-Gaussian state, a crucial building block for quantum computing. Next, the refinery chips, 6 in total, take these non-Gaussian states and refine them into high-quality qubits. They use a clever setup called a binary tree of beam splitters, which acts like a filter to select the best states. The refineries also entangle pairs of photons into a GKP Bell pair, a type of entangled state used in the Gottesman-Kitaev-Preskill (GKP) approach. This approach, which the researchers chose, allows for deterministic operations, meaning they always work, unlike other methods that rely on chance. Finally, the 5 QPU chips take these Bell pairs and entangle them into a larger structure called a cluster state. This cluster state, spanning 86.4 billion modes across the chips, is the heart of Aurora's computing power. The QPU chips perform calculations by measuring the photons using homodyne detectors, which can switch between measuring position or momentum properties of the light. These measurements happen in real time, with results fed back within a single clock cycle to adjust the system dynamically. Aurora's design is modular, meaning each chip handles a specific task, and fiber optic cables connect them. This modularity makes it easier to scale the system, add more chips. The researchers also demonstrate key features for fault tolerance, like real-time error correction using a repetition code and adaptive measurements to fix errors on the fly. While Aurora isn't yet fault-tolerant due to optical losses, it shows the path forward. Let's dive deeper into Aurora's GKP approach. The Gottesman-Kitaev-Preskill method encodes qubits in the properties of light waves, specifically their position and momentum. This encoding allows the system to perform operations using simple room temperature components like beam splitters and photodiodes. Unlike other photonic methods that need cryogenic detectors at every step, GKP only requires cooling for the initial state preparation, making it more practical. The GKP approach also enables deterministic operations. In quantum computing, deterministic means an operation always succeeds, rather than relying on probabilistic outcomes that might fail. For example, entangling photons or performing logic gates in Aurora happens reliably every time, thanks to the GKP method. This reliability is crucial for fault tolerance, as it reduces the chance of errors creeping in. The researchers improve the GKP approach by using macronodes, clusters of entangled photons that act as a single qubit. They entangle these macronodes into a cluster state, a web of connections that allows the computer to perform calculations by measuring the photons in specific ways. Aurora's cluster state spans 12 physical qubit modes per clock cycle, and over 2 hours it generates 86.4 billion modes, a massive scale that shows the system's potential. One of the biggest hurdles in photonic quantum computing is optical loss, when photons get lost or absorbed as they travel through the system. Loss introduces errors, making it hard to achieve fault tolerance. The researchers dedicate much of their study to analyzing and reducing this issue. In Aurora, photons travel through fiber optic delay lines, which buffer them between stages. These delay lines, manufactured by Luna Innovations, currently have an average loss of 0.28 decibels. However, the researchers show that most of this loss comes from connectors and splices between fibers. Using a single continuous fiber, they predict they can reduce loss to 0.03 decibels, or just 0.7%, a considerable improvement. They also stabilize the fibers against temperature and acoustic fluctuations using thermoelectric coolers and piezoelectric shifters, ensuring the photons arrive in the right state. The paper calculates that Aurora needs a squeezing threshold of 9.75 decibels to achieve fault tolerance, a measure of how much the light states must be compressed to keep errors low. This threshold improves on previous estimates, thanks to a 2-layer error correction system that identifies errors and then fixes them using a matching algorithm. While Aurora doesn't yet meet this threshold, the researchers' analysis provides a roadmap for future improvements, like using lower loss fibers or faster clock speeds. Aurora demonstrates several features essential for fault tolerance. One uses a foliated distance-to repetition code, which helps detect and correct errors in real time. The system runs 13.8 million repetitions of this decoding algorithm, showing it can handle errors dynamically. Another feature is adaptive measurements. Aurora adjusts its measurements within a single clock cycle based on earlier results, a process called feed-forward. This adaptability is key to keeping errors in check. Scalability is another strength of Aurora's design. The modular architecture allows researchers to add more chips as needed, increasing the number of qubits. The fiber optic interconnects make it possible to network chips across distances, potentially linking multiple Aurora systems into a larger quantum computer. The researchers also verify entanglement across the system by measuring correlations between photons, confirming that the cluster state maintains its quantum connections over billions of modes. What does this mean for the future? The researchers emphasize that Aurora, while not yet fault-tolerant, lays the groundwork for scalable quantum computers. Once optical losses drop below the critical threshold, photonic systems like Aurora could tackle real-world problems, like simulating new materials or optimizing global supply chains that classical computers can't handle. Photonics modularity and room temperature operation also make them a practical choice for large-scale deployment. This work shifts the focus of quantum computing research. Instead of chasing short-term applications with noisy systems, the field prioritizes building hardware supporting error correction and scalability. Aurora shows that photonics is a viable path to that goal, offering a blueprint for future quantum computers that could change how we solve problems. The advancements in scaling and networking, a modular photonic quantum computer, open up a world of possibilities for quantum technology. If this topic excites you, I encourage you to explore more. Start by reading the full paper in Nature. It's open access and packed with details. You can also check out books like Quantum Computation and Quantum Information by Michael Nielsen and Isaac Chuang, or watch lectures from institutes like the Perimeter Institute for Theoretical Physics. Follow the latest quantum computing news on platforms like Quanta Magazine, or attend virtual conferences like QIP to stay updated. The future of computing is quantum. Dive in and be part of the revolution. What an incredible journey we've had today. We've explored scaling and networking a modular photonic quantum computer, uncovering how the Aurora system uses photons to pave the way for fault-tolerant quantum computing. From its modular design to its battle against optical loss, this work brings us closer to a quantum future. I hope this inspires you to dig deeper into this transformative field. What do you think? Will photonic quantum computers change the world? Share your ideas in the comments. I read everyone. Suggest topics for our next video, give us a like, and subscribe to keep exploring with me. Thanks for watching, and I'll see you soon.